So, we are studying certain properties of random processes which would help us to characterize failure of randomly vibrating systems. So, in this lecture we will be studying how to characterize peaks and extremes of random processes. We will quickly recall what is the things that we did in the last lecture. We characterize the number of times the level alpha is crossed in the time interval 0 to t. That is, if you consider a few realizations of a random process, and if this is the level, then and we focus on an interval say 0 to 1 second, and we ask the question how many times this level alpha is crossed. You could see that for this realization the sample crosses level alpha 6 times, whereas here it is 12 times and here it is again 6 times. That would mean this number is a random variable, and we are knowing the properties of this parent process x of t. We are interested in characterizing the probabilistic obtaining a probabilistic description of these numbers. We set up a counter for counting the number of times the level alpha is crossed, and this counter turned out to be a highly nonlinear transformation on the parent process and its derivative, and the integrand turned out to be the average rate of crossing of level alpha. For a Gaussian random process, we showed that the average rate of crossing of level alpha is given in terms of the variance of the parent process and the variance of the derivative process, and this was the expression that we got, and the variance of a process and its derivative are related to the moments of the power spectral density function. For example, area under the power spectral density function, which is the 0th moment, is the variance of the process, and omega square into Sxx of omega d omega integrated from 0 to infinity, which is the second spectral moment, is the variance of the derivative process. So, we could express the rate at which the level alpha is crossed in terms of the power spectral density, or more specifically the moments of the power spectral density function. So, we will continue this discussion, and we will try to now see if we can make a model for probability distribution function for the number of times the level alpha is crossed in a given interval. I already pointed out that we can find the mean of this capital N. With some effort we could find the variance, but finding probability distribution by applying rules of transformation of random variables is not a trivial task. But under certain heuristic assumptions, for example, if we assume that the threshold level alpha is high, so that crossing is a rare event, and if we also assume that crossing times are mutually independent, then a model for number of times the level alpha is crossed in an interval can be proposed based on a Poisson model for this random variable. So, a Poisson random variable, we know the probability distribution function or the probability mass function is given in terms of a rate. So, this lambda now is actually the rate at which these points arrive, and that is nothing but the rate of crossings of level alpha. Therefore, we have already determined this rate of crossing of level alpha, and hence we can postulate a Poisson model. The only parameter here is lambda, and lambda in terms in fact would be the average of n of alpha comma t. That is for a Gaussian random process, stationary Gaussian random process with 0 mean. We have shown that it is related to variance of the process and variance of the derivative of the process. So, consequently, we can actually write down the probability distribution function for number of times the level alpha is crossed, that is displayed here. So, this is a Poisson model. So, please bear in mind there are the assumptions that we are making is the level alpha is sufficiently high, so that crossings are rare events and the crossing at different time instants are independent. So, then this model is likely to be acceptable. We will continue with our discussion. We will need to now distinguish between what are known as narrow band and broad band processes. So, this band represents a width of a spectrum frequency. So, the description here is essentially in frequency domain. So, we are talking essentially about stationary random processes. To clarify what is meant by a narrowband process and what is meant by a broadband process, we consider a few examples. Let us begin with a function x of t is p cos lambda t plus theta. Let p be a Rayleigh random variable and theta be uniformly distributed in 0 to 2 pi, and p and theta are stochastically independent. Mean of x of t is expected value of p cos lambda t plus theta. Since p and theta are independent, I can express them as product of expectation of p and product of cos lambda t plus theta. The average value of cos lambda t plus theta over 0 to 2 pi is 0, therefore, expected value of x of t is 0. Now, if you consider the autocovariance function, that is expected value of x of t and x of t plus tau, we can write it as expected value of p cos lambda t plus theta plus into p cos lambda t plus lambda tau plus theta. Now, there are two random variables p and theta, they are independent, therefore, this can be written as expected value of p square into expected value of cos lambda t plus theta cos lambda t plus lambda tau plus theta, and you can show that reduces to the term cos lambda tau. So, that would mean this random process x of t is a stationary random process with 0 mean, because autocovariance is a function of time difference. So, the power spectral density of this is actually the Fourier transform, and a power spectral density, for example, if you write it as expected value of p square into 2 pi Dirac delta of lambda minus omega, you can easily check that the Fourier transform of this is nothing but expected value of p square cos lambda tau, which is the autocovariance that we are looking for. That would mean this is the relationship between autocovariance and power spectral density. For power spectral density, now I am writing this p square 2 pi delta lambda minus here 1 by 2 pi expected value of p square 2 pi delta lambda minus omega cos omega tau d omega, which is this, which is okay. How does a sample of this process looks like? So, I will show a graph here. A sample of x of t equal to a cos omega t plus theta will be simply a harmonic function. If a and theta are random variables, the amplitude and phase of the next realization would be different. So, distinct realizations will have different amplitudes and phase, but each realization will be a harmonic function. So, if you look at its power spectral density function, it is a Dirac delta function as shown here. Now, what I will do is a power spectral density is an idealization of what realistically would be a slightly different function. So, if we now consider a realistic narrowband process, for example, if I pass a white noise through a single degree freedom system, we have already studied this problem, and we have shown that the power spectral density here is h of omega whole square into I. Now, if I plot this power spectral density as the damping parameter eta becomes smaller and smaller, this function tends towards a Dirac delta function, but for a finite value non-zero value of eta, the power spectral density function would look like this. That means, this is an ideal narrowband process, whereas this is a realistic narrowband process. How does sample of a realistic narrowband process looks like? It will look like this. This amplitude will be now a kind of a slowly varying function. This is a of t is now a function of time, and theta of t also would be slowly varying in time. The sample will be a kind of a modulated harmonic function. What is an ideal broadband process? An ideal broadband process for example, is a Gaussian white noise. Gaussian white noise can be viewed as an ideal broadband process. So, the mean of W of t is 0, expected value of W of t into W of t plus tau is a Dirac delta function. It is in time, it is Dirac delta function, but in frequency it is a constant. So, if we now look at an ideal broadband process, the power spectral density function is a constant. So, this of course continues, this goes up to infinity. It is constant for all frequencies, that is why it is called white noise. But a realistic broadband process will have a kind of a band limited, it will be a band limited white noise. The variance of this process is unbounded, whereas in reality this kind of power spectral density functions can be idealized as white noise as far as our interest is focused between, say for example, in this problem between 2 to 18 radian per second. If our interest is focused only in that frequency band, this power spectral density, this random process can be viewed as a white noise, but in reality of course it is a band limited white noise. So, how does sample of a broadband process looks like? So, it will be more and more erratic, and if I zoom now say between say 0 to 1.6 second, it will have all frequencies are present. Therefore, at any resolution there will be erratic signals, the signal will be erratic. Now, an example for a band limited white noise would be a power spectral density which is constant for a frequency bandwidth modulus of omega less than sigma, and it is 0 outside. If you look at the Fourier transform of this is sin sigma tau by pi tau. So, we are looking now at ideal narrowband process, realistic narrowband process, an ideal white noise, ideal broadband process, and an ideal realistic band limited broadband process. So, in reality we will be dealing with this and this, but for mathematical idealization we will be using this and this. An important feature of a narrowband process is associated with its distribution of peaks and level crossings. If you consider now a realization of a narrowband process, and if this is the level alpha, this green line is alpha, you will see that every time the level alpha is crossed, there is a peak. See, this level is crossed, there is a peak, this level is crossed, this is a peak. So, this is one of the properties of a samples of narrowband random processes. That means, every 0 crossing with positive slope is followed by a peak. So, if you are interested in studying peaks, you can now imagine that that is associated with study of level crossings for narrowband process. This of course is not true for broadband processes. For example, this is a sample of a band limited process. You can see here, suppose if you focus on this level crossing, there are 3 places where there are extremas, 2 are maxima, 1 is minima. So, similarly here this level crossing is followed by 1, 2, 3 extreme. So, here again you will see 1, 2, 3. So, in ideal broadband process, for every crossing of level alpha, we cannot place a bound on number of peaks that might exist above a given level. So, this is another property that we should now begin to appreciate if we are interested in distribution of peaks. Peaks are associated with highest values of random processes, and they are of fundamental interest in engineering. So, for broadband processes, we can make the statement for a sample of a broadband process, crossing with positive slope can be followed by several extremes. This is in contrast to sample of a narrowband process, where typically every level crossing alpha is followed by a peak. Now, if you focus attention on narrowband process, we can develop a model for distribution of peaks for a narrowband process. This is an heuristic approach. It is not mathematically rigorous, but based on certain heuristic arguments. To explain this, let us consider x of t to be a 0 mean, stationary, narrowband, Gaussian random process. Now, let us consider peaks above level alpha in the interval 0 to t. If I am now interested in the probability that a peak is less than or equal to alpha, this is equal to 1 minus probability of peak greater than alpha. Now, you look at the probability of peak greater than alpha, we can give a relative frequency interpretation for this probability, and we will say that this probability that peak greater than alpha is given by the ratio of number of peaks above level alpha to the total number of peaks. This is a relative frequency definition. So, this can be elaborated as total number of times the level alpha is crossed with positive slope in 0 to t. we have shown that for a narrowband process, for every crossing of level alpha there will be a peak. So, the numerator can be interpreted as total number of times the level alpha is crossed with a positive slope in 0 to t. What is total number of peaks? The total number of peaks is equal to total number of 0 crossings with positive slope in 0 to t. Every time a level 0 is crossed, there will be a peak that gives all the peaks. For example, here if I were to set my level alpha here, we see that this crossing of level alpha does not lead to a peak above level alpha, whereas if you draw this line, the crossing of 0 will lead to this peak. So, once we are interested in total number of peaks, we have to look at crossings of 0, and you want peaks above alpha, you have to look at crossings of level alpha with positive slopes. So, if we do that, we have now the definition for probability of peak greater than alpha in terms of the number of crossings of level alpha and number of crossings of level 0, and this problem we have tackled. Therefore, we should be able to make a model for this probability. So, how do we do that? So, probability of peak greater than alpha is ratio of total number of times the level alpha is crossed with positive slope and divided by total number of 0 crossings with positive slopes. This is given by n plus alpha of 0 t, that means number of times level alpha is crossed in 0 to t with positive slope, divided by number of times the level 0 is crossed in 0 to t with positive slope. Now, we make an assumption, we replace, this is a random variable of course, we replace this by its average. So, we can say it is some kind of an ergodicity assumption, where we are now actually replacing an ensemble average by a sample average by an ensemble average. Now, if we now make an ad hoc assumption that the expected value of this ratio is equal to, approximately equal to the ratio of expected values. This is not generally true, but if we make this assumption, we get now numerator as expected value of number of times the level alpha is crossed in 0 to t with positive slopes, and in the denominator I have number of times the level 0 is crossed with positive slopes in 0 to t. Now, since x of t is a stationary random process, this number will be equal to the rate of crossing of level alpha multiplied by the length of the time duration, because this rate is constant, because process is stationary. So, this t in the numerator and denominator gets cancelled, and I now have the probability in terms of ratios of rates of crossing of level alpha and rate of crossing of level 0, that we have already studied. So, we have now for crossing of level alpha, the rate is given in terms of variance of the parent process and its variance of the derivative process, because x of t is Gaussian, I can write this, and in this expression if I put alpha equal to 0, I get the numerator, and now some of these terms gets cancelled, and I am left with, for this probability, a model which is exponential of minus alpha square by 2 sigma x square. So, consequently, the probability distribution function for the peak can be written as 1 minus this probability, this is 1 minus exponential minus alpha square divided by 2 sigma x square. You differentiate this with respect to alpha, you get the probability density function, and it turns out that this is a Rayleigh random variable. So, we get now a model for peaks of narrowband, Gaussian narrowband processes, and according to this model, these peaks are distributed as Rayleigh random variable. So, the summary is, if you consider a narrowband process, this is the distribution of the parent process, this is Gaussian, that is this blue line, this is Gaussian, and if you look at the peaks, the peak is Rayleigh, this red line is this peak, this is Rayleigh random variable. This is a proposition based on certain heuristic arguments. This model of course is valid only for the situation where process is narrow banded. But how do we characterize the peaks if process is more general? Suppose it is band limited, it is not narrow banded. How will you proceed? That is the next question that we will consider now. So, that takes us to the problem of establishing distribution of peaks for a general random process. So, we consider a random process x of t, which is not necessarily Gaussian, which is not necessarily stationary and which is not necessarily narrow banded. So, it is a general process. I define this quantity m of alpha comma 0 comma t as number of times the level alpha is crossed, the number of peaks above level alpha in the interval 0 to t. Now, the question is, what is the probability distribution function of m? So, we will again look at a few sample realization of a typical random process. Here, how many peaks are there above level alpha? There is one here and there is one here. So, for this sample I get 2, whereas for this sample I get 1, 2, 3, 4, 5 and 6, and for this sample I get 1, 2 and 3. So, clearly therefore, the number of peaks of x of t above level alpha in a given interval is a integer valued random variable. So, if you are given a complete description of x of t, what I can say about this random variable? Can I find its probability distribution? Can I find its moments, mean, variance? What I can do about it? So, m of alpha comma 0 comma t is number of peaks in x of t above the level alpha in 0 to t. It is an integer valued random variable. The problem is, given the complete description of x of t, can we characterize this random variable? This is the problem of determining peak statistics. Mind you, I am not talking about a narrowband process, I am not talking about a stationary process, I am not talking about a Gaussian random process, it is a general random process. Now, let us look at one realization bit more closely. So, this is the level alpha. Now, for this realization in this time interval 0 to 5 seconds or whatever, there are 4 crossings. So, now I need to set up a counter to obtain this 4 mathematically. What I can count visually has to be now translated into a mathematical counter. So, to do that we need to analyze the properties of these 4 points in some detail. So, how do we do that? Now, here I have a series of plots. So, let us begin with the topmost plot. This is the sample realization of x of t. X axis is time and here it is x of t, and the red line here is the level alpha, and I am interested in counting the number of times the level alpha is crossed in the interval say 0 to 5 seconds. Actually, this graph is exactly this graph, but shown on a slightly different scales. Now, I define a process which is x dot of t, which is a time derivative of this blue curve. So, whenever there is a peak, there will be a 0 crossing. So, number of peaks in x of t is equal to the number of 0 crossings in the derivative process. So, we will first use that property. To be able to do that, I define the derivative process. So, wherever there is a peak, there is now a 0 crossing. Now, I define the process u of x dot of t minus 0. That means, I am now interested in actually I want to count the total number of peaks above level 0. So, how many times 0 crossings are 0 crossings occur, therefore, I do this first and then differentiate this. So, I get differentiation of step function is Dirac delta function, this is Dirac delta of x dot of t minus 0 and its double derivative. So, I get a spike wherever there is a crossing. So, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 crossings are there, 0 crossings are there for x dot of t. Now, one is positive, another is negative. To circumvent that, I take the absolute value. So, I take absolute of x dot of x double dot of t into this. So, I get now 1, 2, 3, 4, 5, 6, 7, 8, 9. These are nothing but the crossings here, etc. Now, each of this crossing here is associated with an extreme value here. For example, this is a place where x dot of t is 0. So, there is a 0 crossing, and in this I am counting that also. But what I need to count is, I do not want to count this particular value, I want to count only these red dots. So, I need to count only these 4. So, what I do? I define u of x of t minus alpha. That means, I define another process which takes value 1 whenever x of t is greater than alpha. So, I get here, if you project now this point here, there is a non-zero function. This is the time that process is spending above level alpha, and it is 1 here. Similarly, it is 1 here, and a small stretch 1 here. Now, to get number of peaks during these time intervals when x of t is staying above alpha, I need to multiply this function with this counter. So, then what happens? I will eliminate this I do not want to count, this I do not want to count, this I do not want to count. So, all that get eliminated when I multiply these two. So, I get 1, 2, 3, 4. So, now I got what I wanted. Now, I have to simply sum them up. So, I integrate this function which is product of this and this, that is modulus of x dot of t into delta of x dot of t minus 0 into u of x of t minus alpha into dt. This integrated from 0 to capital T will give me 1, 2, 3, 4. 4 is the answer that I am getting. This is what will happen here. Okay. So, if you carefully see this, the logic is reasonably straightforward. We are using Dirac delta functions and step functions extensively. So, that properties of those functions need to be borne in mind while interpreting this. So, I have now the counter ready for number of times level alpha is crossed in 0 to t in terms of the process x of t, its time derivative x dot of t, and its second derivative x double dot of t. If x of t is displacement, I need property of the displacement, velocity and acceleration. So, the integrand can be interpreted, I denote it as m of alpha comma t. This can be interpreted as rate of peaks above level alpha in x of t. Okay. So, for a fixed value of capital T, m of alpha comma 0 comma t is a integer valued random variable, because it is a counter 1, 2, 3, 4 etc. This m of alpha comma t is rate of peaks above level alpha. This is also a random variable for a fixed value of this lowercase t. Now, if I am given complete description of x of t, that would mean I would be able to write the joint probability density function of x of t, x dot of t and x double dot of t. Given that, and using rules of transformation of random variables, it would still be difficult if not impossible to find the probability distribution of m of alpha 0 comma t. So, finding PDF of m or the rate is difficult if not impossible. So, we can try finding a few moments. So, we begin by finding the mean. So, what is expected value of number of times number of peaks above level alpha in 0 to t is the expected value of this, and the expected value of the integrand is expected value of these terms involving highly nonlinear transformation on the parent process, its derivative and its second derivative. This expectation can be determined if you know the joint density between x of t, x dot of t and x double dot of t. That would mean here I have to write down a threefold integral with integration on dx, dx dot, dx double dot of p x, x dot, x double dot, and this is the function whose expectation is being taken. Now, since I have a Dirac delta function, integration with respect to x dot will be straightforward, and wherever there is x dot I will write it by, replace it by 0, that is what has been done here. And this u of x minus alpha is a step function. So, this can be eliminated from the integrand if we take care to write the limit of integration for x not from minus infinity to plus infinity, but from alpha to infinity, because anyway it is 0 from minus infinity to alpha, because this is a step function. So, this step function gets eliminated, is taken into account, and this Dirac delta function is taken into account, and this triple integral now can be recast as a twofold integral, or this is nothing but an integrand involving the probability density function of x, x dot, x double dot, but x dot is fixed at value 0, and integration limits for x is alpha to infinity. Similarly, we can also find the mean square value. If you are interested in mean square value, you have to find expected value of m square of alpha of 0 comma t. So, from a one dimensional integral, I will now move to two dimensional integrals, and this integrand involving m of alpha comma t1 and m of alpha comma t2 can be expressed in terms of actually a 6-fold integral, and two integrals become easy to handle because there will be two Dirac delta functions, and if you allow for that, I am left with a 4-fold integral involving joint density of x dot and x double dot at two time instants t1 and t2. So, this of course is not straightforward to integrate, but it is a formal representation. Suppose we are interested only in peaks, we are not interested in minima. That means, suppose if we go back to the case of a sample of a broadband process, we saw that here for instance, peaks above level alpha, there are 3 places where x dot of t is 0. Suppose I am interested only in these positive peaks, that is maxima and not in these valleys, then we need to modify the formula slightly. Suppose we are interested only in peaks, that is maxima, we need to restrict second derivative to take only negative values, right. So, the integration in that case with respect to x double dot will be from minus infinity to 0. This is the only difference, this is the difference that will be there because of this change in our statement of the problem. Now, average rate of extrema in x of t, that is all the extrema wherever x dot of t is 0 is average rate of 0 crossings in x dot of t. It picks all the peaks and valleys. So, this can be found out by letting alpha to minus infinity, because if level is at alpha equal to minus infinity, it is crossed always. So, you pick up all the places where the slopes are 0, and we can verify that if I actually compute this expected value of m of minus infinity comma t, if process is Gaussian, is not necessary right now to be Gaussian, in terms of the joint density of x dot and x double dot, we will get this. And if you now relate this expression to the problem of level crossing, you will see that the average rate of peaks above level minus infinity is same as the rate of crossings of level 0 by the derivative process. So, this is consistent with what we have done till now. Now, to illustrate the ideas developed, let us consider x of t to be a stationary Gaussian random process with 0 mean. The problem on hand consists of determining the expected value of peaks above level alpha in 0 to capital T. For this, we need the joint density of x dot and x double dot. Process is Gaussian, therefore, the probability density function will have this functional form, where this matrix S is a matrix of covariances of the 3 random variables. The basic 3 random variables here are x of t, x dot of t and x double dot of t. At the same time t, we are considering 3 random processes. So, S will be expected value of x square of t and expected value of x of t into x dot, x of t into x double dot, and so on and so forth. Now, the process is given to be stationary. So, some of these terms can be shown to be 0. So, if x of t is stationary, you recall expected value of x of t and x dot of t is 0, and x dot of t and x double dot of t is 0. The process and its derivative are uncorrelated for a stationary random process. That is the result that we derived earlier. We have also shown that expected value of nth derivative of x of t and mth derivative of x of t plus tau is given by this expression formula, and that we need to use now to determine expected value of x of t into x double dot of t plus tau. So, if we do all this, the S matrix becomes 4 entries become 0 and the other entries can be determined. This is 0 because we are talking about correlation between x and x dot, and this is 0 because we are looking at correlation between x dot and x double dot. So, these are 0 and this matrix is symmetric. So, equipped with this I am giving a notation sigma 1 square is expected value of x square of t, sigma 2 square is expected value of x dot square of t, and similarly sigma 3 square is expected value of x double dot of t whole square. Now, I can expand this will be the determinant and this gets simplified to this form, and we also need the inverse of this matrix and this quantity x transpose S inverse x. So, inverse determinant is found, the inverse can be found. Following these steps I get the exponent x transpose S inverse x to be given by this expression, and for x dot equal to 0 the 3-dimensional density function between x of t, x dot of t and x double dot of t is given by this expression, because x of t is a Gaussian random process. So, I am writing down the 3-dimensional joint density function. This can now be substituted into the expression for average rate of crossing of level alpha, and this is the expression. Once you substitute this, one of the integration could be done with some effort, but the integration with respect to alpha perhaps need to be done numerically. Anyway, with one integration the expression reduces to this for the rate of peaks above level alpha, and therefore, the average number of peaks above level alpha in 0 to t is given by integral of this rate over 0 to capital T, and since process is stationary, none of these quantities sigma 1, sigma 2, sigma 3 are functions of time. Therefore, I can multiply the rate by the time duration over which you are counting the peaks and I get this expression. So, the problem is essentially solved. Yeah, a few remarks to summarize what we have been saying. This rate of crossing of peaks above level alpha is not a function of time, because x of t is a stationary random process. If we are interested in peaks above level alpha, a few simplifications are possible, but in general that one dimensional integral that remains need to be evaluated numerically. If x of t is a non-stationary random process, then what happens is the correlation between x and x dot is not 0 at same time t. So, the S matrix will be fully populated and the expression for this rate of crossing rate of peaks above level alpha differs naturally, but however this expression can be obtained by using an approach similar to the one that we outlined just now. In this case, apart from the additional complexity in dealing with a fully populated S matrix, the rate of crossing peaks above level alpha would be a function of time, and consequently when we find the expected value of total number of peaks above level alpha in 0 to t, a further integration in time has to be done, that again would require numerical evaluation. Returning to the case of stationary random process, we have now used this expression sigma 1 square, sigma 2 square, sigma 3 square to denote variance of x of t, variance of x dot of t and variance of x double dot of t. These variances can be expressed in terms of power spectral density of x of t as variance of the process is area under the power spectral density, variance of the derivative process is PSD into omega square, the area under that curve, and variance of the second derivative is omega area under omega to the power of 4 into the power spectral density. This is the 0th spectral moment, this is the second spectral moment, this is the 4th spectral moment. Okay. So, that would mean the rate of peaks above level alpha are again getting expressed solely in terms of spectral moments. You may know the joint density function between x of t, x dot of t and x double dot of t, but if your attention is focused on average rate of peaks above level alpha, only things that matter are the spectral moments, 0th, second and 4th order spectral moments. So, thus the spectral moments become important descriptors in discussion of peaks. Now, we can develop a strategy for approximate evaluation of probability density function of peaks above a level alpha in the time duration 0 to t, following the argument that just now we used for a narrowband process. This is more general. Suppose we are interested in probability of peak less than or equal to alpha, this is 1 minus probability of peak greater than alpha, and for the probability peak greater than alpha, if we use a relative frequency approach, we can say that this is a ratio of number of peaks above level alpha in 0 to t divided by total number of peaks above level alpha in 0 to t. This is total number of peaks in 0 to t. So, this is given by m of alpha comma 0 comma t and m of minus infinity comma 0 comma capital T. Again we approximate this by an expected value and bring in an heuristic assumption that expected value of ratio is nothing but ratio of the expected values, which is not true, but we invoke this assumption here. I will be able to now write down the expression that we have developed just now can be now utilized, and the requisite probability now is expressed in terms of average rate of peaks above level alpha and average rate of all the peaks where alpha is set to minus infinity. The expressions for these quantities we have already determined. So, we substitute here and we introduce a parameter denoted by epsilon. We call this parameter as average number of 0 crossings with positive slope per unit time divided by average number of peaks per unit. We have now the expressions for these two quantities, and it turns out that epsilon, using the results that we already have, is given by the ratio sigma 2 square by sigma 1 into sigma 3. Now, if process is narrow banded, every 0 crossing will be followed by a peak, and what happens to epsilon? Epsilon goes to a value of unity. If process is broad banded, in ideal white noise, moment a 0 crossing is 0 crossing occurs, there can be an infinite number of peaks, therefore epsilon goes to 0. So, this epsilon therefore can be viewed as a bandwidth parameter. It takes values between 0 and 1. If x of t is broad banded, it approaches value of 0, and if x of t is a narrow banded process, epsilon approaches 1. But we should be careful here to understand what is meant here. What we are saying is that x of t is broad banded implies that epsilon is 0, but if epsilon turns out to be 0, it does not mean that x of t is a broad banded process. Similarly, epsilon equal to 1 need not mean that x of t is narrow banded. Again, this parameter epsilon can be expressed in terms of the spectral moments, because sigma 1, sigma 2, sigma 3 are all expressible in terms of moments of the power spectral density. Now, proceeding further and using this notation epsilon and with some after some algebraic manipulations, you can show that the probability density function of the peaks is given by this expression where epsilon is the bandwidth parameter, and apart from that the only other descriptor of the parent process will be in terms of sigma 1, which is the sigma 1 square is the variance of the parent process, and the properties of the derivative and the next derivative is encapsulated only in the definition of epsilon. Now, in this case, in this expression, if you put epsilon equal to 0, we get the result that the probability density function of peaks is indeed turns out to be a Gaussian random process. That means there is no distinction between the process and its peaks. For a narrow band process, however, as epsilon goes to 1, one gets a Rayleigh density function for the peaks, and this is quite consistent with what we saw earlier. So, how does this graphically look like? So, epsilon equal to 0 is this result, which corresponds to the Gaussian density function, and epsilon equal to 1 is the limit of narrow banded processes, and in between I have a family of probability density functions where epsilon takes values from say 0.1, 0.25, etc., 0.9 and 0.95. So, as we approach 1, they tend towards becoming Rayleigh, and as approach 0, they tend towards becoming Gaussian. Again, let me emphasize that these results are obtained based on heuristic arguments, and one has to be careful when we use it. The next description of a random process in which we are interested is related to the time spent x of t above level alpha in a given duration. We denote this as gamma of alpha of 0 comma t. This denotes the total time spent above level alpha in duration 0 to t. This is a real valued random variable. Now again the question is, given the complete description of x of t, how can we characterize gamma? If we divide gamma by the total duration, we get a quantity which is known as fractional occupation time. If for entire duration 0 to t, if level process stays above level alpha, the fractional occupation time is 1. If it never crosses level alpha, the fractional occupation time is 0. Therefore, it takes values in 0 to 1. So, we can focus on characterizing this fractional occupation time, and again the question is, if we are given complete description of x of t, can we characterize the probability distribution function of this fractional occupation time? If that is difficult, can we characterize its moments? That is the question. So, what is that we are talking about? This blue line is the sample of the random process and this red line is the level alpha. This is the level alpha, and we are interested in knowing that in 0 to 5 second how much of time is spent above level alpha. So, one episode of time spent above level alpha occurs here, the next episode occurs here, the third one occurs here, and the last one occurs here. So, if you now project these points below, here you see that what I have defined on the y axis here is a step function u of x of t minus alpha. So, whenever x of t is greater than alpha, I define another random process whose value is 1. Okay. Now, if I find the area under this function, the height is 1, I will get the time spent by x of t above level alpha. This height is 1, therefore, the area of all these pulses will give me the total time spent above level alpha. So, y of alpha comma t, which is the fractional occupation time, is given by 1 of t 0 to t and step function of x of t minus alpha dt. Given the nonlinear transformation implied in this step function, again finding probability distribution function of y is difficult. So, we try to find, say, its expected value or its first few moments. So, if you start with expected value of y of alpha comma t is expected value of this integrand, and that takes us into the expected value of u of x of t minus alpha, which is minus infinity to plus infinity u of x minus alpha p x of x comma x colon t dx. So, I am this expression of course is valid for x of t when it is not necessarily stationary, not necessarily Gaussian, not necessarily having 0 mean, is generally valid. Now, if x of t is Gaussian with 0 mean, then expected value of u of x of t minus alpha can be evaluated by evaluating the integral 1 minus infinity to alpha p x of x colon t. This is a Gaussian density function. So, what is required is to find the area under Gaussian density function from minus infinity to alpha, that is expressible in terms of error function. Therefore, I get the expected value of this function to be given by this. This is in terms of error function, and we have the standard deviation of the parent process appearing in this expression. Further simplification of course is possible. If x of t is stationary, then I can multiply the the integrand becomes independent of time, and I can pull it out and I will get this expression where the capital T gets cancelled and I get the average of the fractional occupation time to be given by this expression. We will see how it can be used later when we talk about failures, how this theory would serve characterizing failures. The next topic on our list is description of envelopes and phase of random processes. To motivate you to the basic problem here, we can consider a sample of a narrowband process. An envelope would mean that you have a curve that would pass through the peaks. This is intuitively the notion of an envelope. It is something that can something within which we can enclose a signal is an envelope, something like this. You can see that the process is oscillating lot more than this envelope. So, envelope is a slowly varying function, and we therefore expect that it would be easier to characterize this than the parent process. That is the expectation. The notion of envelope and phase is not new to us, it is widely used in structural dynamics. For example, if you recall undamped free vibration of a single degree freedom system, say the equation of motion is x double dot plus omega square x equal to 0, we can construct the solution as x of t equal to x naught cos omega t plus x naught dot by omega sin omega t. Now, if I substitute for x naught is r cos theta and x naught dot by omega is r sin theta, we can express x of t in this form, where r is square root of x naught square plus square of this quantity, and theta is tan inverse of x naught dot by omega x naught. This r can be thought of as an envelope of x of t here, and this theta is the phase. Here r is greater than or equal to the amplitude of x of t for all t. That would mean if you plot the sample of x of t, this red line is r of t. Actually, this is constant in this case, it is r. Now, if you plot the power spectral density function of this signal, we have already shown that this is a Dirac delta function. On the other hand, you look at the probability distribution of r, it takes one value and that is again a Dirac delta function, but this is probability distribution function. This is PSD. Whereas in PSD I am looking at the frequency distribution, in envelope I am looking at amplitude distribution. That means in envelope I am looking at a value at a given time, the highest value. Whereas in power spectral density I am looking across the time, it is a global descriptor. So now we are moving towards amplitude of the signal which is encapsulated in a probability distribution function and not in power spectral density. If we plot now x dot versus x of t, for this particular sample we will get a closed curve. Here what we have to do is associated with x of t I have to define x dot of t, and for every value of t I have a pair of numbers x dot of t and x of t, and I plot one point here. As the time advances, this trajectory x of t and x dot of t will trace a curve which will be a closed curve because this signal is periodic. You look at now damped free vibration, we can do a similar analysis. I mean this is familiar to us. We can express x of t as this is a solution we get exponential e raised to minus eta omega t a cos omega dt plus b sin omega dt, and the derivative of this is a velocity, and by imposing the given initial conditions we can determine a and b in terms of initial conditions. Now if I make a substitution, a as r cos theta and b as r sin theta, x of t can be written as exponential minus eta omega t into r cos omega t minus theta. So this function can now be interpreted as the envelope. How does it look like? This is r e raised to minus eta omega t, which bounds the blue line is bounded by these two pairs of red lines. So this is the envelope of x of t. In this case, suppose if you plot velocity versus displacement curve, this will be a decaying curve. So it spirals down and eventually it comes to origin. This is the initial condition, and as time passes it will propagate along this trajectory and it will finally spiral down to the origin. Now if you are taking a harmonically driven single degree freedom system, deterministic, we know that the response is characterized in steady state by the static response into a dynamic magnification into cos omega t minus theta, and this dynamic magnification is expressed in terms of the frequency ratio lambda by omega and damping ratio. So, this quantity xst into dmf can be viewed as the envelope of response of the system to harmonic excitation, and there is an associated phase as well. We will consider in the next class what happens if this excitation instead of p cos lambda t is a general force f of t, how to characterize an envelope, and followed by that we will discuss how to generalize this notion of envelope if f of t is a random process. That means x of t is a random process. How do we introduce the notion of an envelope and phase? That is a topic for next lecture. So, with this we will conclude this lecture.